Hello, my math homies. It is time for some trig. So this week we're going to actually use the unit circle and trig identities as our main focus in finding values at certain angles of trig functions. And so you're going to want your unit circle. So hopefully you've filled yours in. If not, maybe you found one online that you could print, but you're going to need this for reference quite often as we work through the assignments. So make sure that you have this ready to go as well. And then, of course, print your notes out. So trig identities, I'm going to give you some new trig identities, which you can see here in the center of the page. And we're going to use these, and I'll show you how we can use them so that we can minimize our work and we're not actually having to do a ton of calculations. But we will want to have these notes handy for the rest of this chapter because trig identities and the unit circle keep coming up even as we dive further into trig functions. So what I would like to do, and so this is all stuff you can read later. This just helps you kind of wrap your head around what it is we're doing today. But these are the identities that we'll be using. And so this is an important one. This is called a Pythagorean identity. And the reason is because you'll notice we have like an a squared plus b squared type situation, right? Well, we know that cosine squared plus sine squared will always give us a value of 1. That is true for any right triangle, for any angle that we're looking at where we can create a right triangle. We also know that, remember, we talked about the reciprocal functions before, that secant is the flipped version of cosine. So that's going to help us a lot when they ask us for instance, like the secant of 45 degrees. Well, all we have to do is find the cosine of 45 degrees and then flip it over. So that's true for cotangent and cosecant. And then this is also a helpful trig identity. Tangent is always equal to sine over cosine. And you could prove that by going back to your SOHCAHTOA and looking at a right triangle. So we're going to use this fact to actually help fill out more information on our unit circle in just a few minutes. So what I'd like to start with is tangent. So we're going to take a look at the relationship between sine and cosine, and that will give us tangent, and we can actually find that tangent value all the way around the unit circle, and if we fill it in ahead of time, it saves us some work later. So knowing that tangent is equal to sine over cosine, we can fill in those values on our unit circle by literally making a division problem. So I want you to look at what I have here. So on the unit circle at 30 degrees, we have a coordinate of rad 3 over 2 and 1/2, right? That's my x value, that's my y value. Well, remember from last week, the x value is the cosine value of 30 degrees, and the y coordinate is the sine value, right? So we know that tangent is equal to sine over cosine. So I'm literally going to take the sine value of 1/2 and divide it by the cosine value of rad 3 over 2. Remember, when you divide one fraction by another fraction, you need to flip the second fraction and then multiply, right? So that's what I've done here. I've rewritten the 1/2, and instead of a division bar like this, I've made it a multiplication, and then I've taken the bottom fraction and flipped it over. And now I'm going to multiply straight across the top and straight across the bottom. However, you can, sorry, I covered that up. You can cancel the 2's, right? You can cross cancel when you multiply fractions. So you end up with 1 over rad 3. Now, this is a perfectly acceptable answer. I just want you to know that when we're actually taking like a paper or a written test, and when you get into calculus in college, this will be acceptable. Traditionally, however, we have rationalized denominators, meaning I'm not allowed to leave a radical in the denominator. It's kind of an old-fashioned concept, and it's starting to phase out. However, in Pearson, when you go to pick your answer, this won't be there. It will be the rationalized version. So I want to show you how to rationalize the denominator really quickly. We've done some of this in class, so I'm just refreshing your memory. What I have to do is get rid of the radical in the denominator. To do that, I'm going to take that 1 over rad 3, and I'm going to multiply by rad 3 over rad 3. Remember, rad 3 over rad 3 is truly just 1, right? So I'm not changing the value of my fraction, but I am manipulating it so that I end up getting rid of the radical in the denominator. So if I chose rad 3 because that is the denominator of my original answer, right? If I multiply, basically I duplicate the denominator, I know that that will get rid of it. So when I multiply by rad 3 straight across the top, I get rad 3. When I multiply by rad 3 straight across the bottom, I get rad 9. Well, what is the square root of 9? That's just 3, right? So notice this is the same exact value. 1 over rad 3 is the same as rad 3 over 3. It's just been rationalized. It's been manipulated a little. So the tangent of 30 degrees is rad 3 over 3. And that's what you're going to see in Pearson when it asks you for something like tangent of 30. So here's what I want you to do with your unit circle. So we just said that the tangent of 30 is rad 3 over 3. What I would like to do is go around and write the tangent values on the outside of each of the coordinates. And then you will have cosine, sine, and tangent right at your fingertips, right? So what happens when I take this y value, this sine, divided by this x value or cosine, right? So notice they're the same, right? Rad 2 over 2 divided by rad 2 over 2. Well, when you have the same value on the top and the bottom of any fraction, you know that that should equal 1, right? What is 10 over 10? What is 60 million over 60 million, right? Well, what is rad 2 over 2 over rad 2 over 2? It looks complicated, but it's the same idea. Well, we know that that's 1. So in this case, the tangent value is 1. So I want you to keep going. And in fact, the best thing to do, let's talk about what happens at the y-axis and the x-axis. And then I think I would like you to pause and fill in the rest, take a few moments. But when we go ahead and we look at this, for example, so sine over cosine, we know that tangent is equal to the y over the x. That is 1 over 0. Well, what happens when you have 0 in the denominator? Remember, you're never allowed to divide by 0. It doesn't happen. It doesn't exist. You can't take something whole and divide it into 0 sections, right? You can't separate it into 0 parts. That's just not possible. So when you have 0 on the bottom, you know that your tangent value is undefined. Undefined. And then what about on the x-axis here? So when you take the y-coordinate divided by the x, so that's 0 divided by 1. Well, 1's on the bottom, that's okay. 0's on the top. What's 0 divided by anything? It's still 0. So your tangent value is going to be 0 here. Now, I want you to do this one at 60 degrees, and then I want you to think about what this means when you look at quadrant 2, and then quadrant 3, and then quadrant 4, right? Do you have to do the division work again in these other quadrants? And I'm hoping you're shaking your head. Nope, I don't, because everything's a reflection, right? We know that whatever answer I get here, it should be very similar to this one. What will change, though? Notice this is a positive divided by a positive, so your answer will be positive. However, your tangent value over here should be negative, right? Because that would be a positive y value divided by a negative y value. So I would like for you guys to finish this. So you should pause now, and then when you're done filling it out, hit play again, and then you can look and see what whether your values match mine. So we're going to take a quick moment to pause. Hi, Jay. You ready to do some math? All right, so hopefully your values match mine now. So I want you to just take a look and make sure we have everything the same, because you don't want to make a mistake on Pearson just simply because you made one quick error here, and that way you can correct it now. But notice, I want everyone to notice that when you get close to, let's say, the y-axis, this is a reflection across the y-axis, right? Now the only difference is your signs. This is going to be a positive rad 3, this will be a negative. Same here, right? Positive, negative, positive, negative. So when you're in your quadrant 2 and quadrant 4, your tangent values should be negative. When you're in quadrant 1 and quadrant 3, they should be positive because they both have the same sign, correct? And when you divide a negative by a negative, you get a positive. Okay, So knowing all your tangent values, it's going to make things a lot easier when we have to calculate the trig functions at the different angles around the unit circle. So let's go back to our notes for a moment. And so I'm hoping you completed the rest, right? Just like we said. And now we're going to get into some example problems. So let's go ahead and try this first one. So using your unit circle, I want you to find all 6 trig functions for 135. So 135 degrees. So you go to your unit circle, you need to find 135 degrees, right? So we always start here at the positive x-axis. This is 90 up here, and you can see 135 is in quadrant 2. So I already know cosine, sine, and tangent. Very easy, right? So let's go ahead and write those out. Because we know those, we know that, I'll change color here. We know that the cosine value for 135 is going to be the x-coordinate. So negative rad 2 over 2. The sine value at 135 is the y-coordinate, which is positive rad 2 over 2. And now we know the tangent value at 135 is negative 1. Okay, so what do we have left? Well, the other 3 trig functions are secant, cosecant, and cotangent. So let's start with secant. So secant of 135 is, now if we look at our notes, so here's all our trig identities, right? Secant is the same thing as 1 over cosine, which what that means is it's the flipped version of cosine. So whatever cosine value is, so the cosine value is negative rad 2 over 2, I'm going to flip that over. So negative 2 over rad 2 is going to be my secant value. Now remember, in Pearson, we have to rationalize the denominator. So that means I need to go ahead and multiply both the top and bottom real quick by rad 2 over rad 2. And the reason we're doing that is because we're not allowed to have a radical in the denominator. Like I said, old-fashioned, but we still have to stick to it when we're dealing with multiple choice tests. So when I multiply straight across the top, I get negative 2 rad 2, and straight across the bottom would be rad 4. What is the square root of 4? Well, that's going to be 2, right? And we have negative 2. Sorry, guys. I just got a new little dog, and he's very yappy. So what happens when you take 2 over 2 on the outside of that radical? Well, you get negative 1. So negative 1, I don't even need to write, but my final answer is just negative rad 2. So really, there's no fraction left, right? So I know that secant of 135 is negative rad 2. Okay, what about cosecant? CSC 135. Well, cosecant right here is the flipped version of sine. So let's go back to our paper. Sine is rad 2 over 2. If I flip it over, we'll be doing the exact same thing we did here. Now, what's different? This one was negative, right? Sine is positive, so that means cosecant should also be positive, and it will just be rad 2. And then the last one is cotangent. Cotangent of 135. Well, cotangent is 1 over tangent. So that means I just take the value of tangent, I put it under 1, right? I flip it over. Well, I know that tangent is negative 1. So 1 over negative 1 is equal to negative 1. So in that case, cotangent and tangent actually have the same value. All right, so you can see all 6 trig functions, we got them, right? I did a little bit of work for secant because of the rationalizing the denominator. But other than that, we're using our trig functions and we're just doing lots of flipping, right? Okay, next problem. We want to find the value of cosine alpha. Don't worry about the change in Greek letters. It's all the same. You've got theta, you've got alpha, you've got beta, all these different Greek letters. The only thing that matters is that it's a variable. So just consider it like an x. It doesn't change your work or your understanding of what you're doing. So I just wanted you to be familiar with that before you looked at Pearson. Okay, so find the value of cosine given that sine is equal to -4/7 and alpha is in quadrant 3. A lot of information coming at us. When you're only asked for cosine and you're given sine, we can use one of our other actual trig identities, and that is the relationship between sine and cosine. So it's really slick to know that if I squared sine and I squared cosine and I added them together, I would get 1, right? Okay, so let's look at what we've got here. So I know that I'm looking for cosine, so we're going to call that x. I have sine, they told me that, -4/7. So plus -4/7 squared equals 1. So I just want you to take a moment and see what I did. I took this trig identity, cosine squared plus sine squared equals 1, and I filled in everything I know. Well, I know the value of sine. I'm calling cosine just a variable, x, and I know that the trig identity is equal to 1. That's where the 1 came from. Now I have an equation I can solve, right? So let's go ahead and do that. Let's square the fraction. Oh, I should have squared the x, I'm sorry. So x squared plus -4/7 squared equals 1. So now I have x squared plus, well, -4 squared is 16 and 7 squared is 49. So 16 over 49 equals 1. Well, how do I get x squared by itself? The best way to do that, subtract your 16 over 49, right? So I don't have a ton of room, so I'm going to kind of work this sideways. I apologize. So now you have x squared equals 1 minus 16 over 49. Well, in order to subtract fractions, I need to make the denominators common. And since this is 1, I can easily turn it into 49 over 49, right? Okay, so take a moment, make sure you understand where I'm getting all these values. So I turned the 1 into 49 over 49, subtracting 16 over 49 so that I can get my x squared by itself, right? All right, well, what is 49 minus 16? That is going to be 33, right? So that means x squared is equal to 33 over 49, but I need it to be x, not x squared. So all I need to do is square root both sides. So when I square root both sides, I'm going to take the square root of each, the top and the bottom independently, right? Well, here's the thing. The 33 doesn't square root, and that's okay. We can leave that as a radical in the top, but 49 does. So that means my denominator is 7. So x is equal to the square root of 33 over 7. Now, here's where we know the cosine value is rad 33 over 7. This is where the other part of our information comes in. So in this case, I know that the angle is in quadrant 3. Okay, so let's just refresh our memory on the quadrants. So we've got quadrant 1, and then we go counterclockwise, 2, 3, and 4. So if I look at quadrant 3, what do I notice about the cosine and the sine values all in quadrant 3? They're all negative, right? So that means that my answer should also be negative because of the quadrant 3 thing, okay? So that's important, and I wish I had a highlighter handy. I would highlight this information, these two things together. Quadrant 3 means my cosine value is negative, okay? So that's important. Okay, next question. Find all 6 trig functions for theta equal to 570 degrees. All right, the reason I wanted you to see this problem, it's going to be very easy. You've done something very similar. But 570, when you go to look at your unit circle, you'll notice that it only goes up to 330, but then if we go all the way to the end, we go 360, right? That's one whole time around. Well, where is 570 then? Remember that all of these angles can be named an infinite number of ways, right? This 30-degree angle could also be called 390. And why is that? Well, because I could go one whole lap around and then 30 degrees, right? So I could go 360 plus another 30 to get 390. I could call that 390. I could add another 360 to that and another 360. So do you see how I can call this angle, just an infinite number of values, right? I can just keep adding a lap around. Well, that's what they've done with 570. They're making you figure out where the actual angle is. So the best way to handle that is to take your 570 and let's subtract out our laps around. So in this case, it looks like we just did one whole lap around and then ended up on our angle, right? Because 360, we don't have more than one 360 in 570, if that makes sense. So when I subtract 360 from 570, I get 210. So that means that 570 is the same as the 210 degree angle. So now let's go back. Look for 210, there it is. So now they're asking me for all 6 trig functions here at this value, right, at this angle. So we can do that. So we know that cosine of 570 is going to be the x-coordinate, negative rad 3 over 2. And we know that sine of 570 is the y-coordinate, which is negative 1/2. And now we know tangent pretty easily because we figured it out earlier, right? Tangent is a positive rad 3 over 3. And then you have the last 3, the secant, the cosecant, and the cotangent. All right, so with these 3, however, there's going to be, or not necessarily all of them, but we might have to rationalize denominators. So I'm going to do that assuming you're okay now with what we have done with our rationalizing. So I'm not going to necessarily show you every step in detail. So secant means I have to flip this over. It's negative, it stays negative, right? If cosine is negative, then secant should be negative. If sine is negative, so should cosecant, right? So your reciprocal functions will have the same sign, but they won't have the same value necessarily. All right, so secant means negative 2 over rad 3. So what I did is I flipped it, right? It doesn't matter where your negative sign goes. It can float as long as you just continue to identify this value as negative, right? Well, when you have the rad 3 on the bottom, we need to rationalize. So I'm multiplying by rad 3 over rad 3, and I get negative 2 rad 3 on top and 3 on the bottom, because remember this becomes rad 9, and then when you take the square root, you get 3. So my final answer is negative 2 rad 3 over 3. Okay, so that's probably the ugliest value of all 6 trig functions that you will see on our unit circle. Now, cosecant, I flip it over, right? So negative 1/2 flipped over is negative 2. And then tangent, same thing. We can flip it over. So this is a positive value because in quadrant 3, remember, tangents are positive, right? So that means cotangents are also positive. So 3 over rad 3, but again, I got to rationalize. So I'm going to quickly multiply by rad 3 over rad 3, and I get 3 times rad 3 on the top over 3 on the bottom, but notice these 3's cancel, and you're left with just rad 3. So there are your 6 trig function values based on 570. So remember, if it's bigger than 360, just subtract your 360s, subtract your full laps out, and that will tell you where you land on your unit circle. All right, last problem. This one requires that we don't necessarily use the unit circle, because what it's telling us is these are coordinates. Notice 3, negative 4. You don't see that here, right? It's telling us that we're going to have a hypotenuse that's larger than 1. We can still use the same trig identities to help us solve these, this particular question. But I don't want you to get totally hung up on the unit circle. We can still create, knowing what we know about the unit circle, we can recreate this exact scenario. So the point 3, -4 is on the terminal side of an angle theta in standard position. So all that's telling us is that we're going to draw an angle in the XY axis, right? Standard position means we would have started on the positive x-axis and we'll open to whatever theta, we have, and then we want to find each trig function. So I'm going to draw a little diagram for us. So we know that 3, -4 would be in this quadrant. So 3, -4. The way we handle this is we connect, so this is our terminal side, right? We connect our dot, our 3, -4, back to the origin, and then I connect this dot back to the nearest x-axis, not the y-axis, the x-axis. So I connect it back to make a nice right triangle. I should have hit my 3 there, but I'm a little sloppy here. We'll just make it a really thick line. Okay, there's my right triangle. Now, what is this length here, this side? Well, we know that's 3. We know this length here is -4, right? The length is 4, but we're going to call it -4 for now because we're in quadrant 4 here. Okay, what do I need to do now to find my hypotenuse? Well, we can use Pythagorean Theorem, right? So that means that we have a squared plus b squared equals c squared. You might also recognize this as a Pythagorean triple, meaning we have right triangles that are perfect whole numbers for all 3 sides, and they're usually multiples of 3, 4, 5. But if you're not sure, you can always go back to Pythagorean Theorem, right? So 3 squared plus 4 squared equals c squared. Now that's 9 plus 16, which is 25, and that tells us that c is 5. Okay, so your hypotenuse will always be a positive number, but your sides, your x and your y, could be negative, right, depending on the quadrant we're in. So that's important to remember. So now all we have to do is go back and find cosine, sine, tangent, secant, cosecant, and cotangent. All right, well, cosine, remember this is our angle here. Cosine is adjacent over hypotenuse, right? So that's a +3 over a +5. Sine is opposite over hypotenuse, so that's -4 over 5. Tangent is opposite over adjacent, so -4 over 3. So you'll see how some of these trig functions will be negative and some will be positive depending on which sides you're utilizing. Now secant, we can go back to our trig identities. Secant is the flipped version of cosine. So that just means we flip it over. It's now 5 over 3. Cosecant, the flipped version of sine. So that would be -5 over 4. And yes, I did move the negative sign up top just because it's pretty traditional to do that, but you could have kept it down below, that's fine. And then tangent and cotangent are flipped versions of each other. So we get -3 over 4. And that's all you have to do. So don't worry about all the wording that they give you. Plot the point, all right? And then create your right triangle. And just label the triangles with the coordinates they gave you. You should know which side is represented by your x and which is by your y. And then use Pythagorean Theorem to find your hypotenuse. And then you can find the rest of your trig functions. It really is that easy. Okay, if you have questions, please don't hesitate to email or ask, and I will be happy to help you work through any of the problems. This week you have 2 Pearson assignments, but they are both based on these notes. So you don't have another video and you don't have another set of notes. You have 2 review assignments, but they're both short. So good luck to you.